Hello AP. Now we're getting to the good stuff of learning how to draw not only Lewis structures, but we're mostly going to be talking about covalent bonding. Okay, so 8.5, drawing Lewis structures. It's very important that you know how to draw any molecule that AP throws your way. And in 8.5, you're going to see some practice AP problems, and I'll work them out with you. Please have a periodic table near you because I'm going to show you one of the coolest methods. Me and another teacher named Miss Aguilar that taught at Fohive many years, we came up with a method to really help students draw very quickly, okay? Instead of showing every single dot, showing arrows, how they go from here to here to here. Don't need it. If AP doesn't ask you to show the formation, they just say draw the Lewis structure, then this is all you need. We called it the Nas method, okay? And no, I'm not talking about the rapper named Nas. So if you know who I'm talking about, then you're probably laughing at this. Nas is a way to look at valence electrons from the periodic table, okay? So basically, how many do they have and how many do they need, okay? So when you're doing this, as I said, have that periodic table near you. And while I'm showing you, because the majority of the notes is sample problems, while I'm doing this, you need to see how I'm pulling these numbers, okay? So it's a helpful calculation to determine the total number of bonds and molecules and hints on how to draw it. So this tiny little calculation, and I don't want you to get too crazy excited because you're like, oh my gosh, I get to touch a calculator, it's been so long. Yes, but you should be able to do this math without the calculator, okay? So this cool calculation is to figure out how many bonds are in the whole molecule, okay? So let's talk about the rules. The N is called needed. Now, every element needs 8. Every element is trying to complete their octet rule. So when you do the calculation, the need is 8. I'm just going through the rules first, then I'll show you how to do it. There are some exceptions, but the math will still work. Hydrogen only needs 2 because he can only form one bond. All he has is one valence electron, so the most he can do is get another electron from another atom. That's it. So all he can do is form one bond. Beryllium, he's in group 2, so he has 2 valence electrons. So if you have beryllium with an electron on each side of his symbol, the most he can do is form those 2 bonds. Now remember, every bond is 2 electrons. So if you count up this bond on this side and this bond on this side, I see 4 electrons, okay? It's very important that you know the exceptions to the rules. So beryllium can only ever have 4 electrons surrounding him, 2 on one side, 2 on the other. Boron, and I'm going to put on here just like aluminum, but we're not talking about any metals, but I just want you to know aluminum still is in this scenario because in group 3, they have 3 valence electrons. So the most boron can do, 3 valence electrons, most he can do is 3 bonds. 1, 2, 3. That's it. So the most he can have ever surrounding him is 6. So the point is, ladies and gentlemen, before you start getting lone pair crazy, start putting dots all over the place, you need to remember what elements need what and what elements have exceptions, okay? So you know I hate that nasty word memorize, but unfortunately you got to know which elements are some exceptions. And I don't think that's a long list. I think that's pretty simple enough to know which ones do this, okay? So that's your need. Your need, everybody needs 8, okay? Wow, I did not mean to go like pink on that. Let's go like different color. All right, there we go. Available. This is where you and Mr. Periodic Table, you got to look. How many valence electrons are available? How many valence electrons do they actually have? Excuse me. So that's why you need a periodic table next to you. And then we get to the shared. what you're going to do is you're going to take these two numbers, N minus the S. You're going to take those two numbers and you're going to subtract them. Now, once you get this number, I'm going to show you what it is. The need minus the available. About 99% of the time, this is going to be an even number. And I wish it was 100 because, man, I would patent this cool thing and make it the Nash-Rodriguez law. I wish it worked all the time because it's very cool. But there always are those exceptions. So maybe it'll be the Rodriguez theory of Nash. Okay? You have to remember this key fact right there. For every 2 electrons, you form a bond. So what we do is we take this number once we subtract it and we divide by 2. And we divide by 2, whatever this number comes out to be, is how many total bonds are in that whole molecule. There's no guessing now. You know where, if it has 4 bonds, you know that whole molecule is 4. So whatever this number is, that is the total bonds in the whole molecule. And that is freaking cool. The part is where you have to figure out is where those bonds are. That's where it can get a little tricky. So when I learned how to draw, I learned the old school way of using the arrows and showing where every single dot goes. Well, for some students, that just doesn't work. This method really does help. And majority of the time, AP just asks you to draw it. That's what they want, okay? So at the very end of this, and I'm going to actually get a little sneak peek so you can see, these are 3 past, and these are within like the past, 3 years, 4 years. So right here, this is 2015's. They gave you the symbols. You just had to draw where the bonds and lone pairs are. Pretty simple. They've been doing this a lot lately, which is awesome because it takes out a lot of the guesswork. You had this molecule, S2Cl2. Figure out what the Lewis structure is. It just says complete the Lewis dot diagram. It does not say show how it forms. Here's the next one. Same year. This is what killed me this year, but it was awesome because we did good at this. They actually had you draw 2 structures, and usually they only have you draw 1. So there's always a drawing question. Could there be more? Absolutely. It happened in 2017. Okay. So this one, you had, what was that, nitrous acid. Complete the dot structure. Pretty easy peasy. Okay. So we are going to go and learn how to do this. And as you see, like I said, there's a lot of practicing. So some key rules to this. When you're drawing, identify the central atom. Now, when a central atom has other bonds around it, the central atom is usually written first. So like, for example, like CO2. The carbon is in the center. Or if I would give you something like, I'm trying to think of one without hydrogen. If I had, I know I'm throwing like a blank right now. Carbon, 4 hydrogens, okay? Carbon still is first. This is methane. You should remember his name by now, methane. But the reason why I was trying to avoid the hydrogen is if you start with hydrogen, okay? So say it's something like HNO2. Just because it starts with hydrogen, hydrogen is never, ever, ever a central atom. It doesn't make sense. He can't get to octet. Never, ever. We'll never get to that octet because look what we just set up here. Hydrogen can only get up to 2. So if you have a hydrogen, he will always be what's called a terminal. And the word terminal means an outside, a surrounding atom. Okay, he will always be an outside atom. So then the question is, well then who's the center? Usually the next element written next is the center. Okay, and that means that the N would be the star of the show. Okay, same thing with like water. What if you had H2O? Well, I see hydrogen written first. Same thing. Can't be in the center. Doesn't make sense. So then you go to the next element called oxygen. And we know what water looks like by now. We've drawn them many times in chapter 4. So central atom, usually the first one. Okay. So usually written first. I'm just going to highlight a couple things. Write all the other atoms around that central atom. Okay, sounds pretty simple. According to Naz, how many total bonds are in the molecule? So this key calculation tells me where every single line I need to draw in the whole molecule. But the question is where am I going to draw those bonds in that molecule? So first, place one bond, that means 2 electrons, between every atom, okay? If you have more bonds to add, you've already put one in between every atom and the other element sitting right next to it. Then that means if you have more bonds, then you could have what's called multiple bonds, doubles and triples. So let's do a little side note over here. You can have what's called single bonds, and I know I lectured on this in 8.3, where you would have only 2 electrons shared in between it. So 2 electrons shared. If you have a double bond, you literally have 2 lines, looks like an equal sign, but you're sharing 4 electrons because every bond is 2. And the most you can ever have is a triple. And that means that there's 6 electrons being shared. So what happens is the strength of the bond changes and the length of the bond changes. So just a little side note, okay? Single bonds are very long bonds, okay? But they're also very weak because they only have 2 electrons basically supporting them, keeping them together. But a triple bond, these are very short bonds. They're very close to each other. And because they're very close together, they're very strong. So you usually need a lot of energy to break through this guy. Whereas a single bond don't need as much energy. Okay, but you always need to remember, and I'm making sure I say this correctly, April, before you call me out on it. Okay, you always need energy to break bonds. Always, always, always. It's always an endothermic reaction. Okay? So anytime you're going to break through bonds, you need energy. So at triple bonds, they are very strong bonds because they're very close together. They're short bonds. And because they're so close together, you need a lot of energy to break them. Okay? Once you've added your bonds, figure out if you need doubles or triple bonds. Not a lot of molecules do, but some do. After that, here comes the lone pairs. So you need to remember the octet rule. Every element wants 8. But remember, there are some exceptions. There are some exceptions. Those guys, beware, beware. And there's others, like aluminum, or if we were drawing other metals, but we're not drawing metals in here. I don't like how AP sticks beryllium in here because beryllium is a metal and he should not even be in this discussion. But AP does bring beryllium in because he does have a little bit of characteristics of nonmetals, very little, but it is known that he has some nonmetal characteristics. Okay, so that's why they kind of throw him in here. Hydrogens are always written on the outside, so there's that fancy word terminal. But here's the key part. I don't want to ever see lone pairs. Hydrogen can only have 2 electrons, which means the most he can ever have, the most, is 1 bond. So you will never, ever see lone pairs ever on a hydrogen. Okay? You will not see lone pairs on boron. You will not see lone pairs on any of these guys. So I'm also going to put it right there too. So what happens is if carbon has 4 valence electrons and I want to bond it to 4 hydrogens, okay, well, it's not rocket science what's going to happen. Every hydrogen has 1 valence electron. And we're talking about covalent bonding, which means they're going to share these electrons. And now that you've learned 8.4, how are they sharing them? Are they equal or not equal? So in a more butyrized, and I just made that word up, okay? A more clean version of this molecule. CH4, that's what it looks like. So you always need to double check. Does your carbon have 8 surrounding electrons? And yes, because in each one of these bonds, there's 2 electrons. 2 electrons, 2, and 2. But does the hydrogen have 8? No. Hydrogen will never have 8. All he needs is 2. So what they're doing is they are sharing these electrons, and every hydrogen is sharing those electrons. So what you see is this thing called orbital overlap. This is where a little bit of organic chemistry comes in a little bit, because carbon is sharing them, hydrogen sharing them, and now that you've learned chapter 8.4 called polarity, question is, are they being shared equally? And yes, because if you do the electronegativity difference, carbon's 2.5, hydrogen's 2.1. Let me make some notes about that. So if carbon had an electronegativity value of 2.5 and every hydrogen's 2.1, you don't have to do the calculation 4 times. You just need it once. So when you figure out these electrons, you subtract, you get 0.4, and that is nonpolar. And what does that mean? It means that the electrons are being shared equally. And I apologize, I'm like cramming that in there in that corner. So if any elements are sharing electrons, now that we know how to figure out if it's being shared equally or not, we just need to look at those electronegativity values, okay, which you should get that beautiful periodic table by this weekend. So here, let's practice, okay? So here it is, short key. Your need, everyone needs 8. Your available is what valence electrons they have right now according to the periodic table. And to find out what they're sharing, we subtract, okay? So we are going to subtract those 2 numbers. And like I said, right now, life is beautiful. It should be an even number, okay? We divide by 2 because every bond is 2 electrons. And this number will tell me the total number of bonds. Okay? So I left this little box right here because I left this area so you can do NAS, okay? Or do it in the margin. That's fine too. But I'm going to show you how to do the NAS for each one. But like I said, have a periodic table near you so you understand where I'm getting these values. Okay? So here we go. I have bromine twice. So bromine, I'm going to list the symbol. Need. Everyone needs 8. But I have 2 bromines. I don't have 1. So I'm going to multiply that by 2. And that means I need 16 electrons. But what do I have? What do I have available? Well, according to the periodic table, there's 7 valence times 2. So that's 14 electrons. Okay? You always have to multiply if you have more of them than just 1. Okay? So I'm going to subtract, and I have 2 electrons being shared, and I'm going to divide by 2, and that means that there's 1 bond in this structure. Okay? Bromine twice, diatomic. Okay? I'm going to write the symbols right next to each other. You don't have a central atom, you got 2 bromines together. And I just figured out I only have 1 bond between them. So I'm going to draw a bond. And now here comes, make sure everybody meets the octet as long as it's not one of those crazy 4. So right now, this bromine is sharing 2 electrons. This bromine is sharing 2. So I need to put a whole lot of lone pairs. And now I have 2, 4, 6, and they're sharing 7, 8. And this bromine, 2, 4, 6, sharing also 7 and 8. And you just drew your first molecule using NAS. Good job if you got it. But let's try one with hydrogen. Okay? Let's go straight for the gusto. H, and I'll do my math over here since I write huge. I'm going to draw it for hydrogen, and I'm going to do it for, I got to do the math for hydrogen and iodine. So need. Hydrogen needs 2. He doesn't need 8, okay? And then, oops, sorry. I want to show that a different way. You'll see why. Okay. I'm going to put my symbol for hydrogen and my symbol for iodine on top instead. Okay. Hydrogen needs 2. Iodine needs 8. I'm not going to multiply it together. I'm adding it together. Over here, it's the same thing as saying 8 plus 8. I just said 8 times 2 because that's all I had was bromine times 2. So if you have more than one element, you're just going to add them all up. So I need 10 electrons in this structure. But what do I have? Here comes valence. Hydrogen has 1 valence. Iodine has 7. Add that up. Subtract. Divide by 2. 1 bond. Okay? And I know you're thinking, is it always 1 bond? No, it's not. Okay? I'm starting with the little guys first before I get to the big guys. So you don't have a central atom because all you have is H and I. And I know I got 1 bond between them. Now the last thing is lone pairs. Do I put lone pairs around hydrogen? And you better not have any dots near that guy. Okay? He can't do more than 2. And right there, there's his 2. There's his bond. But iodine needs 8. He needs to fill the octet rule because remember, he's got 7. He wants to gain that electron. And that's it. That is your structure for HI. Let's do another one with hydrogen, but with 3 of them though. Okay? So right here, I'm going to do my NAS, and I'm going to put it for nitrogen and for hydrogen. Nitrogen needs 8. He needs it, he needs it. But hydrogen needs 2, but I don't have 1 hydrogen, I have 3. So it's like adding 2 3 times, or you can just say multiply by 3. But I'm going to add those together, and 8 plus 6 is 14. And I really hope I don't screw up in math in this, ladies and gentlemen, because you know Rodriguez is known to make a little boo-boo there, here and there. Nitrogen has 5 valence electrons. Hydrogen has 1. But I still have to multiply by 3 because I got 3 hydrogens and each one has a valence electron. So 5 plus the 3 is 8. I'm going to subtract, and I'm going to divide by 2, and now I have 3 bonds. See, I told you it's not always 1. So I have 3 bonds, so 6 divided by 2, 3 bonds. Now you have to figure out who's the central atom, because you have nitrogen and 3 hydrogens. Remember I told you, the first atom, central atom. And I'm going to put 3 hydrogens around it. Usually I go left and right first, and then I put the third one either top or bottom. Doesn't matter which one, you get to have a choice in life. But I have to have 3 bonds, and I got to make sure I have a bond between every element. So now the last thing is lone pairs. Do hydrogens get lone pairs? Nope. Does hydrogen, or does nitrogen? I got 2 here, I got another 2, and another 2. So right now I'm looking at 2, 4, 6, and nitrogen does need a lone pair. So 7 and 8. Okay? I know you're getting it, but I know you're thinking, okay, I just need to see it some more. Okay, let's keep going. Phosphorus and chlorine. Okay? Phosphorus and chlorine. Phosphorus needs 8. And I do have chlorine, but I got them 3 times. So I got to go 8 times 3. Okay? I'm going to add that up. And what is that? 8 plus 24, so that's 32. I'll just put them over here since I'm out of room. And what does phosphorus have? Well, he's sitting right below nitrogen, so he's got 5 valence. And chlorine has 7, but times 3. Okay, that's very crucial that you don't forget those subscripts. So 21 plus 5 is 26. I'm going to subtract. Like I said, if you need that calculator, okay, but I think you should be able to do this without the calculator. And we're going to have 3 bonds. Who's the central atom? Phosphorus is the first one, so he's the star of the show. And I got to put 3 chlorines around it. Okay? Got to have 3 bonds. 3 chlorines, 3 bonds. 1, 2, and 3. Does phosphorus need lone pairs? Well, look at phosphorus. How many does he have around him right now? He's got 2, 4, 6, so he definitely needs 1 lone pair. But what about each chlorine? Right now, every chlorine is sharing 2, so they need a lot of lone pairs. 2, 4, 6, sharing 7 and 8. But you have to do that for each chlorine. So notice how dark the dots are that I'm making. You need to make sure when you're drawing, especially with the pen, with the stylus, that those dots are very dark. Okay? I know we know what water looks like, but I want you to see how cool the math works. Okay? So with hydrogen and oxygen, hydrogen needs 2, but we have 2 hydrogens, so times 2. And I'm going to add that to the 8 that oxygen needs. Okay? So 8 plus 4, that's 12. And hydrogen has 1 valence, but times 2. And oxygen has 6 valence electrons. So 6 plus 2 is 8. Subtract, divide. I got 2 bonds. Now who's the star? It's not hydrogen. He's never in the middle. So you go to the next element called Mr. Oxygen. You're going to put a hydrogen on each side. And I know you know what it looks like. But are you drawing the true structure when we did chapter 4 and you didn't? Because you didn't show me lone pairs. I need 2 bonds, but if you're checking out oxygen, right now he's got 2 on this side, 2 on this side. He's only got 4. He needs 5 and 6, 7 and 8. That's what water looks like as a Lewis structure. Okay? So now that's how we're drawing water. Now if they want a particle diagram, then yes, you draw your water with your little Mickey Mouse ears. Okay? That's a particle diagram. This is a Lewis dot structure. Okay? So I'm going to even write that down because when I ask it, I'll know I definitely told you. So particle diagram, Lewis dot structure. Okay? Now I'm going to throw beryllium in here because like I said, AP has been known to throw him in here and I do not like that they do that. But we can't always like everything. Beryllium is one of those exceptions. Remember, right up here. Beryllium, okay, he's only ever going to form 2 bonds, okay? So what happens is when you get to his need, okay, he only needs 4, okay? Because remember right up here, beryllium only wants 4. Now, you're probably thinking, well, how am I going to remember that? Okay, well, remember, how many valence does he have? He has 2 valence. So 2 times 2, that's all he can do is 4 electrons surrounding him. Chlorine needs 8, but times 2. So 16 plus the 4 is 20. Chlorine has 7 valence, but times 2. So 14 plus 2 is 16. Subtract, divide, 2 bonds. So you know beryllium is the star, and you got to have 2 bonds and a chlorine on each side. Okay? So if you get kind of lost on what they need, some of these exceptions, look at how many valence they have and what's the maximum they can hold. Beryllium only has 2 valence. That's it. Bond, bond, done. End of story. He will not get any lone pairs because he can't. He can't hold more electrons because he only has 2 valence to give. So, but the chlorine are very happy to take those electrons from beryllium. So they will have lone pairs. Boron and iodine. I want to do a couple of these exceptions to the rules because I wanted to make sure that you guys have them in your notes. Boron is that exception. Okay, he can only need 6. That's it. Because he only has 3 valence electrons. Iodine needs 8, but times 3. So 24 plus 6 is 30. But he has 7 times 3. 21 plus 3 is 24. Subtract, divide, 3 bonds. Boron's the star. 3 bonds 3 iodines. Will boron get lone pairs? Don't you dare, because remember we said he only needs 6. He's fine, he's happy, leave him alone. But the iodine, they all need their 8. And there you go. Okay. We just drew carbon with 4 hydrogens right above. Okay. Just like this. But try the math. You try the math. See if you can actually get the math to be 4 bonds. Okay. That's what it's going to look like. But you do the math. Okay. So set it up as your NAS. How many carbons? How many hydrogens? But don't forget, hydrogen, there's 4 of them. So times 4. CH2Cl2. Okay, now we got 3 elements to take a look at. Carbon still, he's still going to be the star of the show. He's got his own chemistry called organic. He's always going to be in the center. So right here, need and available, I have to do 3 of them. C, H, and Cl. Carbon needs 8. Chlorine needs 8 times 2, but hydrogen only needs 2. But there's 2 of them. So 8 plus 4 plus 16. So I'm doing math in my head. Here we go. It's late at night and I'm doing math in my head. 16 plus 4 is 20 and then 28. Carbon valence is 4. Hydrogen is 1 times 2. Now chlorine, a halogen, has 7 but times 2. So 14, 15, 16 plus the 4 is 20. Subtract, divide, 4 bonds. Now I got 2 hydrogens to put around him, and I got 4 bonds that I need. 2 chlorines. So this, ladies and gentlemen, is when you call, I have options. And anytime you have options, you want to keep the same elements away from each other. So I'm going to put maybe my hydrogen right here and put it all the way on the other side of the carbon. If you got options, get them away from each other. Chlorine on the top, chlorine on the bottom. However, they need lone pairs. So chlorine, iodine. I need some lone pairs up there. And this chlorine needs his lone pairs. Does hydrogen get lone pairs? Never. Is carbon okay? Does he have his 8? 2, 4, 6, 8. Done. He's happy. Okay? And what if you have 2 carbons, 6 hydrogens? Okay? Anytime, I even gave you a little side note, when you have only carbons and hydrogens, the carbons align themselves as the central atoms, which means both carbons are sitting right next to each other, and all the hydrogens go all around it. Okay? But let's do the math. So carbon needs 8 times 2. Hydrogen needs 2, but times 6. Okay? So 16 plus, let me do this down here because we're going to make this molecule big. So need, available, carbon needs 8 times 2, and hydrogen needs 2, but times 6. So 16 plus 12 is 28 electrons they need. Now what do they have? 4 times 2 plus 1 times 6. Just looking at valence electrons. So I have 8 plus 6 is 14. And then 14 divided by 2, 7 bonds in here. Okay? Now, 6 hydrogens, and I automatically have to have a bond between the carbons. And I got 6 more left. I got 7 total, but 6 more. I got a hydrogen and a bond. I got another hydrogen and a bond, and another hydrogen on this one. I can't put any more hydrogens on carbon because that's it. You cannot have more than 8. So 2, 4, 6, 8, that carbon's happy. Leave him alone. Now go to the next carbon. Here's a carbon and a hydrogen, carbon and a hydrogen, carbon and a hydrogen. Now double check him. This carbon right here has 2 on top, 2 over here, 2 on the bottom, and he's sharing these 2 with the other carbon. He's happy. He's good. The point is, ladies and gentlemen, the NAS method, it works. It really helps students see it without drawing every single dot and arrow and showing me where they go. That takes time. And in AP, we don't have any time unless AP says draw the formation of the compound. Okay? I hope you like it. And no, the notes aren't over. Don't get too excited. Okay? Because I need to show you some other ones. Now let me show you what's called multiple bonds. So now you're going to start to see some doubles and triples. Okay? So still do the work. Still do the NAS. It helps. And before I get this question, do I have to do NAS? I could see it without it. Fabulous. Great. Do it. But if you don't do NAS and get it wrong, I'm just going to say now, I told you so. Okay? Take the time, do the NAS, until you become that expert that can do it without the NAS. I've been doing this so long, 20-something years, I can see it without having to do NAS. But I'm showing you so that way you don't get it wrong. I'd rather you do this quick little math than screw it up and get it wrong. Because we don't have those points to lose. Oxygen needs 8 times 2. So 16 electrons are needed. He has 6, but times 2. 12. Subtract, divide. There are 2 bonds. Now, all I got is 2 oxygens, and I got to put a bond, and that is my only spot right there to put bonds. I need 2, so I create what's called a double bond. Okay? Now, right now, I'm looking at 4 electrons in the middle. So what does oxygen need? He needs 4 more electrons. Now, remember this thing called options? When you have options, get them away from each other. So I need lone pairs, but I only need 2 sets. So I'm not going to put it on the side because the point of lone pairs is they're loners. They're non-bonding. They don't want to be near anybody. So you get them away from each other. And same thing on this one. I need lone pairs on that oxygen too. What about nitrogen diatomic? Okay. So nitrogen diatomic, I have 8 times 2, 16. But nitrogen has 5 times 2. Subtract, divide. Now he's got 3 bonds. No brainer. I got 2 nitrogens sitting by each other. Triple bond. How many lone pair? Well, right now, I'm staring at 6 electrons right there in those bonds. So if they have 6, I need another 2. And do I have options? Yes. Get them away from the bonds. So we're going to put them on the sides. Okay? When in doubt, you have options, get them away from each other. Okay? I'm doing these 2 because these have been known to show up on the AP test before because they have multiple bonds. Okay? It's not like this one up here. See how this one has 6 hydrogens? This one has 4. This one has 2. Okay? So you're going to see the multiple bonds. What I need for carbon is 8 times 2. And I'm going to add that to the hydrogen and 2 times 4. So 16 plus the 8, so that's 24. Now carbon has 4, but times 2. And this carbon, this hydrogen has 1 times 4. So I have 8 plus the 4, and that's 12. Subtract, divide. Did I do something wrong? 8 plus 4, 16, 8. Okay, no, sorry. I had a little brain fart there. Okay. Now, remember this rule right up here? When you have more than one carbon, the carbons align with themselves. Okay, so we're going to put those 2 carbons next to each other, and they automatically have to have a bond. But now I have 4 hydrogens. So what you want to do is put 1 hydrogen on top and bottom for this carbon, and they form a bond. And on this carbon, do the same thing. Well, if you count, that's not 6. So where is the 6th one? Because right now I'm staring at 5. Hydrogen can never do double bonds or triples. It doesn't even make sense. Look at hydrogens. They can only do 2. So your 6th bond is right there between the carbons. Okay? Now count it up. Does carbon need lone pairs? Well, look at this carbon right here. I got 2 on top. Here's 3 and 4. 5 and 6, 7 and 8. He doesn't need lone pairs. And this carbon right here, 2 on top, 2 over there, 2 on the bottom, 2 on that hydrogen. He's good. He's happy. Leave him alone. You will rarely ever see carbon with lone pairs. It's probably, you will never see it in AP, but it's definitely, we see it in OChem. So that's for another science next year. Okay. C2H2. Let's see what happens when we take another 2 hydrogens off. So carbon, 8 times 2. Add it to the hydrogen, that is 2 times 2. So 16 plus 4 is 20. And then available, it's about the same math, 2 times the 4 plus 1 times 2. So 8 plus 2 is 10. And subtract and divide. I got 5 bonds. I got 2 carbons, so they're going to align with each other. Now I only got 2 hydrogens, so I got to spread them out. I'm going to put 1 hydrogen over here, and I'm going to put 1 hydrogen on this side. Remember, when you got options, spread them out. I'm not going to put them on top or bottom because then they'll be close to each other. So I automatically have to have a bond between those carbons and hydrogens. Well, remember, we just did the math. 5 bonds, and I'm only staring at 3, whereas the other 2, called a triple bond. Fill it in between the carbons because hydrogens can't do more than 2. So now you're looking at carbon and thinking, well, do I need any lone pairs? Well, count it up. Right there, I'm staring at 6 electrons. And I got another 2 on this side. That carbon's got 8. Same thing over here. Staring at 6. There's 2 over there. That carbon's good. You're not going to see lone pairs on carbon. Very, very rare. Okay? Now you're probably thinking, well, Rodriguez, can you draw ions? Absolutely. My law works. But let me show you. Don't forget to address the charge. So let's look at ammonium. How does the math work? Okay. So I'm going to move my little note a little bit up there. Okay. Little trick when it comes to that charge. Remember, this charge right here means he lost an electron. Okay, well, the math still works. We just got a little added step. Nitrogen needs 8. Hydrogen needs 2, but times 4. So right there, that's 16 electrons. Available, nitrogen has 5 on the periodic table. Hydrogen, 1 valence, but times 4. Look at what that just became. Oh, we haven't seen an odd number ever. So here's what happens. Remember this part right here? He gets affected when you get to the available. He doesn't have 9 available. You lost an electron. You lost it. You lost it. You subtract 1. You don't subtract from the need. You need 16. You're subtracting from the available because you don't have 9. You have 8 electrons available. So that right there is because of the charge. Math still works. 4 bonds in this structure. Don't think it's rocket science. I got nitrogen, 4 hydrogens. I need 4 bonds, 4 hydrogens, 4 bonds. I think it's pretty evident. But now you have to show me somewhere in this structure it lost an electron. So what happens is, this is really the reality of what happens. Nitrogen has 5 valence. And I got a hydrogen that attaches on here, a hydrogen attaches there, a hydrogen attaches there, and you're like, well, what am I going to do? One of these lone pairs, they split. And he takes a hydrogen. And look at that lonely dot. Bloop. That's the +1. You lost an electron on nitrogen. So what you do is you put this whole structure in a bracket. Not a parenthesis, a bracket. And you put the charge in the corner. So you're just telling me in this entire molecule, I lost an electron somewhere in this molecule. So when it comes to charges, you got to put the structure in brackets with the charge in the corner. Okay? I just want to show you a couple of these so that way you see that the math works. Okay? So for OH, And somewhere in here, I gained an electron. So for need, oxygen needs 8, hydrogen needs 2. So that's 10 electrons. For available, oxygen has 6, hydrogen has 1. See where that odd number comes in? But remember, I gained an electron. So I have to add an electron to my structure, and there's my even number. Subtract 2, divide 2. There is one bond only. All I got is an O and an H. There's my hydroxide. O and H. Remember, don't put the H first. There is none of those in chemistry. Okay? But I need to check the octet. Okay? For this oxygen, I'm only looking at 2 for oxygen. So he's going to need some lone pairs. And I didn't disregard this one over here. Nitrogen, he's already got his 8. Hydrogen never gets 8. So it's all set. I need my brackets and my negative on the outside. Okay, so that's what it looks like. Let me show you a couple others. Cyanide right here. Nitrogen. Oh my goodness, I even said nitrogen. NOS, the need and available. Carbon and nitrogen. Each one needs 8. 16. But what do they have? They have 4 and 5. And what does that -1 mean? That means it gained. So it gained. This is when it gets tricky, because I know you're thinking, oh, I'm going to put -1. No, he gained. So we got to add 1. So there's our 10. Subtract, divide. There are 3 bonds between 2 elements. It's called a triple bond. Before you get crazy with the brackets, double check the octet. Carbon's looking at 6. He needs lone pairs. Nitrogen's looking at 6. Lone pairs. Remember, when you got options, get them away from each other. Lastly, put it in brackets. Charge on the outside. Okay? Nitrogen monoxide. Nitrogen needs 8. Oxygen needs 8. But what do they have? 5 and 6. But he lost an electron. He lost, so we take one away. 10, subtract, and divide. 2 elements, triple bond. Okay? Do they have their 8? And no, they don't. Okay? Nitrogen needs his lone pairs. Get them away from those bonds. And oxygen needs his lone pairs. Brackets, charge. Hopefully you're loving this, ladies and gentlemen. I know you're not loving the time, but hopefully you're like, Rodriguez, I'm getting this. I'm liking this. It's definitely better than explaining trends in Chapter 7. Oh, I know you're agreeing with me on that one. Okay? However, we need to finish this up. Very hard topic, but I think you're going to get it. Okay? If you can draw, you should be able to get this. Okay? The name of the game is this. Let's take a little moment. It's called formal charge. When we draw a structure, we are describing how the electrons are distributed in the molecule or the ion. In some instances, we can draw more than one possible structure, and all of them have to obey the octet. The problem is, it's the multiple bond ones. Sometimes, who says it has to be a double or 2 doubles bonds between it? So like something like this. Let's say we did the math, and the math told us, so when we did the NOS, so I'm just saying if we did the NOS and it came up to be 4 bonds, and you had this mysterious compound that looks like this, or molecule, since we're talking about nonmetals. Well, it says 4 bonds, and I got 2 oxygens surrounding this X. Well, who says it has to be a double and a double? I'm looking at 4 bonds. Why can't it be something like this? Why can't it be a triple and a single? This is where formal charge comes in. You have to figure out which structure is something called the preferred structure. And that's where formal charge is. Formal charge is a calculation which one is preferred? Does the molecule prefer to have 2 on each side, or does it actually prefer to have a triple and a single? Okay, so let me show you the rules. All of these structures can be thought of as contributing to the actual arrangement of the electrons in the molecule, but not all of them will contribute to the same extent. So what happens is it's a blend of them, but one of them is what's called the dominant structure. Because I can even say this. Why can't this side be the single and this side be the triple? So you're looking at 3 possible structures, but only one of them is the preferred dominant structure. So some important things we have to keep in mind. The formal charge of an atom in a molecule is the charge the atom would have if all the atoms in the molecule had the same electronegativity. This is in that wonderful world where everybody had the same electronegativity, everybody wanted the electrons the same, life is beautiful, everyone's the same. Okay, we know that's not it, but that's the point of formal charge, is if this was a magical world and every atom had the same electronegativity, that means they all shared them equally, if, this is a big if, okay? Formal charge is not a real charge. It's a calculation. It's a bookkeeping system to figure out which structure is preferred. Okay, oops, preferred. It's useful when comparing 2 Lewis structures in which the atoms obey the octet. So to calculate this, because I want to show you how it's calculated. All unshared non-bonding electrons are assigned to the atom. So we're talking right here non-bonding. We're talking about the lone pairs. All unshared electrons, aka the lone pairs, are assigned to only that atom. However, if you have a bond, single, double, or triple, what you do is you cut the bond in half. So let's say I had this, oops, sorry, didn't mean to put in highlighter. Let's say I had this X, and let's use that structure that I did on top, okay? You would cut these in half, just like that, and that's really bad cutting in half. Sorry about that. Let's make it a little longer. You cut them in half. And what formal charge is saying is this: half of the bonding electrons are assigned to each atom in the bond. So these 2 sitting right there, they go to oxygen. And these 2 in the bond, when you cut it in half, they go to the X. Same thing over here. Trust me, it's going to make sense once you see what I'm doing. So you cut the bonds in half. Half of the electrons go to O, half the electrons go to the X. So here's the calculation. You take the number of valence electrons for that atom and you subtract it to what's called assigned. Okay? You want, this is what we want. We want that number to equal 0 for the formal charge, because that means it's preferred. Every atom that has a 0 is a preferred structure. So if all atoms in the molecule all have a formal charge equal to 0, then what that means is that structure, out of all of them, is the preferred structure. Okay? So let's take cyanide. Okay? There is no other way to draw cyanide besides that. Okay? Because you're probably looking at it as like, how am I going to move triple bonds around when there's no other atoms to move them around to? It's not. But I chose cyanide because I want you to see how the math works. Okay? So this is the magic equation right there. So formal charge equals the valence minus assigned. Okay? So when you set up your calculation, carbon has 4 valence electrons, nitrogen has 5. Okay, because Mr. Periodic Table told me so. But what's assigned? So first, cut the bonds in half. And remember, I have 3 on this one, and I have 3 on this one. So what's assigned? Look at what you're looking at carbon. I have these 2 lone pairs on carbon plus 3 electrons from the bonds, so I got 5. And this nitrogen has the 2 lone pairs and these 3 electrons on this part of the bond, so he's got 5. You subtract the numbers. 0, and because it's a charge, as in plus or minus, it's not a true charge, but because you're taking 4 minus 5, you will get a negative number, and that's okay. So the name of the game is, if all of these were 0, that's the preferred structure. But you can't draw cyanide another way. It can't happen. You have to have another atom, like 3 at least, to actually be able to figure something out like this. I'm just showing you the math first. You know the example's coming. So notice, the sum of the formal charge equals the overall charge. So this is very key right here that you're seeing this. Remember, cyanide is Cn -1. Notice this. -1 plus 0 equals that charge. They have to equal the charge that's on the molecule. So whatever all these equal, it has to equal the charge on that molecule. Okay? The formal charge of a neutral molecule means that they all have to equal 0. So if you don't have a charge on that molecule, like say water, then it has to equal 0. That means the formal charge of hydrogen has to be 0, added to oxygen has to be 0. It's got to be 0. Okay? Water's probably not the best example because there's no doubles or triple bonds in it. So, very key fact, you would only be doing this calculation if you have what's called multiple bonds. And I mean you actually see doubles or triple bonds. All right, apologies, phone ring. Okay, so water would not be the greatest example here because you only do formal charge if you have multiple bonds like doubles and triples. So like my example of like CO2, okay, I can actually draw carbon with 2 oxygens on each side, or I can draw it with triples and singles. So only do formal charge for multiple bonds. Very, very key. I don't want you wasting your time if all you have is single bonds, because that's it. All the formal charges are 0. So in this, let me show you, as I said, there's CO2. So if we can draw several Lewis structures for a molecule, the concept of formal charge can help us decide which is the most important, aka the preferred dominant Lewis structure. One Lewis structure for CO2, for instance, could have double bonds. However, you could also have singles and triples. Okay? So calculating formal charge is like this. Okay? So if I had CO2, I would cut those bonds in half, just like that. And now valence. Well, according to Mr. Periodic Table, oxygens have 6 valence, carbon has 4. So just like over here, 6 and 4. But now assigned. So now you got to count it up. You have lone pairs on this oxygen, top and bottom. So that's 2, 4. But remember, you're taking 2 electrons from that bond and giving it to oxygen. So there's your 6. 6 minus 6 is 0. Carbon has these electrons from the bond and has this 2 electrons from that bond. He has no lone pairs. So there's your 4 minus 4, still 0. And this oxygen over here, 2 lone pairs. So there's 2 and 4. And then the 6 coming from the 2 bonds. So 6 minus 6. This is definitely the dominant structure, because all formal charges are 0. But I want you to see why this one is not the dominant structure. So if I take this in half and give each one of these the electron, this oxygen has 6 electrons surrounding it, plus the 7 from the bond, so you get a -1. Carbon's still looking good, formal charge 0. But this oxygen over here, if you have a triple, he's getting 3 from the bonds, but 2 from the lone pairs, so you get a positive. Because remember, it's valence minus assigned electrons. And notice right there, they're not 0. Okay, so this is not the dominant structure. It's what they call the minor. There's a topic called major structure versus minor structure, and this should just be a minor structure. It's a different possible structure, but it's not the dominant structure. Okay, so it's a possible structure. Okay, but not the dominant. Also, remember this rule right here, right there at the top? The formal charge for a neutral molecule has to be 0. Check this out. CO2, carbon dioxide's got no charges. -1, 0, +1, all together equals 0. So you always want to make sure when you do this calculation that if that molecule does not have a charge on it, they have to equal 0. So when you're doing guidelines to this, if you have a molecule in which each atom obeys the octet rule, the most preferred structure is the one that each atom has 0. Has 0 for every atom with a formal charge. If you have a polyatomic ion, the sum of all the formal charges will equal the charge on the polyatomic. So say you had something like phosphate, PO4, -3. When you do the formal charge, all of the formal charges have to equal that -3. Okay? If it's not possible for each of the atoms to have a formal charge of 0, then this is what we like to call like the tiebreaker. Okay? Sometimes you have to use this rule. The most favorable structure is the one that has the negative formal charge on the atom that's most electronegative. Okay? So if you're like, man, I don't know if it's this one, I don't know if it's that one, so then you come to this rule. Okay? Like I said, it's like the tiebreaker sometimes. If you have a negative formal charge on the atom, it has to be on the highest electronegative value. So remember, the highest electronegative element is fluorine. And then you got oxygen that's sitting right next to it, and you got chlorine sitting next to it. So out of the highest electronegatives is fluorine, but then you got oxygen and chlorine sitting right next to it. They definitely, you're going to want to try to see negative formal charges for them, because everybody else surrounding them are less electronegative than those three. CO2 is the dominant structure that has the 2 double bonds on it. The other Lewis structure shown, it's similar with the triple bond to the left and the single to the right. It contributes to the actual structure, but it's a very smaller extent. Like I said, it's like a minor possible structure. The major structure would have the 2 double bonds. Okay? So although the concept of formal charge helps us arrange Lewis structures in order of importance, it is important that you remember that formal charges do not represent real charges. It's a calculation to determine the preferred structure. And I remember when AP did this too. Okay? So let's do some examples. Determine the formal charge in each structure based on the formal charges, which structure is the dominant charge. And I just took this example from the book, page 318. So let's do the math. So right here, it helps if you set the calculation up just like this. Valence minus assigned. Okay, so we're going to do this structure right here. So valence electrons minus assigned electrons. Okay. So, for all the valence, look at the periodic table. Nitrogen has 5 valence, carbon has 4, sulfur has 6. These numbers will not change. Okay? But what's assigned will. So we got to cut these in half and look at what is on each side. So I like to usually draw little dots until we get the hang of this. Nitrogen right there, he looks like he has 7 assigned to him. So look at him. He's got 7 surrounding him. So 5 minus 7 That's -2. We're already looking bad as it is right there. Not even close to 0. Carbon, he's got 4 around him, -4. So there's 0. And this sulfur right here, remember there's 3 on this side. I got 3 plus these 2 over here, so I got 5. So +1. Already not looking good, okay? But now let's try this one. What if it's a double and a double? So if we cut these in half, and I go ahead and just put my dots on each side, okay? Nitrogen, 2 on top, 2 on bottom, 2 on the right. So he's got 6 assigned, -1. So looking a little better. Carbon, then again, like I told you, very rare you're going to see a formal charge of anything but 0 on carbon. And sulfur, 2 on top, 2 on the bottom, and then 2 on the left side, and 6. That looks much better, okay? So definitely not going to happen, okay? But let's try this one. What if it prefers to be a triple and a single? So if I cut it in half, okay, put my 3 dots over here, 3 dots on this side, and this single only has 1 on each side. So nitrogen has the 3 from the bonds plus the 2 on the left, so 5. All right, looking good. This carbon, 3 from the bonds plus this one on the right, looking good. Sulfur, 2 on top, 2 on bottom, 2 on the right, but you got to count that 7th one right there. So -1, okay? And I just want to make a little side note. Remember, if this formula is NCS -1, look at all these formal charges. All of this equals -1, equals -1. All of this equals -1, even though not even close to being the dominant structure, okay? Because you have 2 atoms with formal charges, not 0. So 2 atoms, what I like to call non-zero formal charges, okay? AP did this 1 year recently where they asked you to explain why it's not the dominant structure. And they said using formal charge. And I'll show you that question, okay? So now here comes the name of the game. Here comes the tiebreaker. If you have one of the atoms that's not 0, we want the negative formal charge to be on the most electronegative, okay? So now we need to bring our periodic table up, and let me grab him. All right, voila, here we go. The 2 that are the tiebreaker is this nitrogen -1 or this sulfur -1. So whoever is negative, the preferred structure is the negative on the most electronegative. So right here, I'm looking at nitrogen, has an electronegativity of 3.0. I'm looking at sulfur, and there it is. There's the tiebreaker. Nitrogen is more electronegative than sulfur. So because nitrogen is more electronegative, and please do not abbreviate that, I'm just out of room here, more electronegative than sulfur. So the dominant structure is this one right there. And I don't want you to think, ladies and gentlemen, it's always when it's equal bonds on each side. It doesn't, there's not a rule about something like that, okay? You have to do the math to figure it out. So the most dominant structure is this middle structure with the 2 double bonds on each side. So because nitrogen is more electronegative than sulfur, the formal charge of -1 needs to be on that nitrogen, okay? Let me show you another one. What if we have cyanate, which is NCO -1? And let's do the math for it, because I don't know what the structure looks like off the top of my head. So if we do the NOS, and we got nitrogen, carbon, and oxygen. So nitrogen needs 8, carbon needs 8, oxygen needs 8. So we got 8 times 3, almost put 16. 8 times 3, 24 electrons. And for nitrogen, valence electron has 5, carbon has 4, oxygen has 6. And when you add that up, you got 9 plus 6 is 15. But remember, gained 1. So we got to add 1 to it. so 16. 24 minus 16 is 8. Divide by 2. There are 4 bonds in the structure. So now we're going to draw it. N, C, and O, okay? And they have it in this order on purpose, okay? So you are going to literally write it, oops, sorry, N, and then the carbon, and then the oxygen, okay? So that is the way that they have it written, okay? Usually, like I said, the first one listed is the central atom, okay? But what this is, cyanate, is usually looks like this, OCN minus. It's looked both ways before on the AP test, okay? But in this case, they wrote it this way. They want it in this order. If I come up with 4 bonds and I only got 2 locations, so here's where it comes to, could it be a double and a double, or could it be a triple and a single? But here's the problem, okay? Who says the single or who says the triple can be on this nitrogen, okay? What if the triple was over here on the oxygen? Okay, a little bit different than when we did up here, okay? You have to be able to move it around if the atom is different, okay? So we're going to do that also. We're going to put it, the single triple bond on this side, okay? Problem is we need a lot of lone pairs, okay? So we got to fix the lone pairs first so we can do the math. So nitrogen right here has 2, so he needs 3 sets of lone pairs. Carbon has 2 on one side, 6 on the other. He's looking good. This oxygen's only sharing 6 of them, so needs some lone pairs. Now remember, it's a charge, so you got to put this structure in brackets, negative on the other side. Okay, same thing over here. Nitrogen, he's sharing 4, so he needs 2 lone pairs on top and bottom. Carbon has 4 on one side, 4 on the other. He's good. Oxygen only has 4, so he needs 2 lone pairs. Same thing, put it in brackets with the charge. And this nitrogen is sharing 6, so needs a set of lone pairs. Carbon's good. This oxygen needs 3 sets of lone pairs. And then negative charge. Okay? So I'm going to move my NAS a little bit out of the way so we can do our math. So we need valence electrons versus assigned electrons. Okay, so first look at the periodic table. Nitrogen has 5 valence, carbon 4, oxygen 6, and these numbers will not change. Okay, so now assigned. So if it helps you to do it in a different color, that's fine with me. Just remember on the AP test, all you get is a pen and a pencil, and that's it. Okay, so I kind of do that. I cut it in half. So I have a dot on each side, and then I got 3 on each for this one. So nitrogen has the 6 surrounding it in lone pairs, plus that one is 7. So already looking bad with negative 2. Carbon, 3 on one, 1 on the other, so 4. And oxygen, 3 on the left, 2 on the right, has 5. So plus 1. Not looking good. Okay, I could probably tell you that ain't the dominant structure. Nitrogen right here, 2 on top, 2 on the bottom, plus these 2. So I got 6, so minus 1. Carbon, 2 on each side, so 0. Oxygen, 2 on top, 2 on the bottom, 2 on the left, so 6. Looking pretty good. So now, I guarantee you, you're probably going to get the same numbers, just that negative 1 is going to be on a different element. It's probably going to be on oxygen, okay? So right here, nitrogen has got those 3 plus 2 on the left, so looking good, 5. Carbon's always going to look good. And then oxygen, 2 on top, 2, 2, plus that one right there, negative 1. See, I told you. So now the name of the game is this. Not even close, not even close. But now we have a negative on nitrogen versus oxygen. Who is more electronegative. Okay, and remember I told you the trick. Fluorine's the most electronegative, and you got the two elements sitting next to him. They are the second most electronegative. And I don't even need to look at the periodic table because I know he's sitting right next to fluorine. And that right there is going to make it the dominant structure. Okay, so this one is going to win. Okay, so see, I told you it's not always the dominant structure is when you have equal bonds on each side. So because oxygen is more electronegative than nitrogen, he's the dominant structure. And that literally is how you explain it, like word for word, as we said. Since oxygen is more electronegative, okay, make sure you can spell that, ladies and gentlemen, then nitrogen, the dominant structure. Okay, if AP says the word preferred, then you say the word preferred. You usually say the word dominant. The dominant structure is in triple bond, C single bond. Okay, and you'd have your lone pairs. I like cram that in there. Apologies, is that one. Okay, so that, ladies and gentlemen, is how you figure out the dominant structure. So this is what I want you to do. Okay, these are past AP questions. I want you, this is no video, you have to figure out yourself. AP may give you a skeleton structure and ask you to fill in the missing electrons, bonding and non-bonding. So this was 2015, 5 years ago. They said the Lewis dot structure was C2H4 as shown in the box on the left. In the box on the right, complete the dot structures, okay, and drawing in all electron pairs. But electron pairs can be bonding or non-bonding, okay? I don't know why they just didn't draw a double bond right here, but even the answer key said you can do that. Same thing right here. There should be a bond here, bond there, bond there, bond there. Okay, so you don't have to draw dots all over the place. So you figure out what's the Lewis structure look by this. Do the NAS, figure it out. Okay, so if you do the NAS, that's the formula that you need to do it for. Same thing for this one, 2017. Draw the Lewis dot structures, drawing in all electrons. Okay, bonds and lone pairs. And here's where the evil one was. Okay, I just didn't have the rest of the question on here. This structure can be drawn another way. AP asked you to draw the Lewis structure for this, including lone pairs of electrons. Okay, but then the evil question that came, they asked about formal charge. So what happens is there's a double bond somewhere in here and some single bonds. So you had to see you on the next one, ladies and gentlemen.